talk. Our next talk will be efficient utility improvement. Oh, sorry, I was looking at the wrong side. The Onion name system, Tor-powered decentralized DNS for Tor Onion services by Jesse Victors, Ming Li, and Zhenwen Fu. Welcome, Jesse.
How's my, I think the audio is good, right? Okay. So, yeah, I moved up and down with the thing, yeah. So yeah, as you said, thank you, and good afternoon. This is my project, our project, and this is the Onion name system, or Onions for short. It's abbreviation. It's essentially a meaningful domain name service for 20 Onion services, solving a long open problem. I believe it has solved a long open problem in that space. Its authors are Jesse Victors, is me, and from Synopsys, Ming Li from University of Arizona, and Zhenwen Fu from the University of Central Florida. I've set aside, of course, some questions at the end. Let's see. So then, next slide. Oh, sorry. So our motivation for our work is that, as most of us probably know, onion sites are simply not practical. This is an example from Wikipedia. These are online, this is the URLs, they're listed here. And when you even visit it in the browser, you have this incomprehensible URL that is, it looks completely random. Of course, as we probably know, it's based on cryptography. And currently, the current protocol, this is 16 characters in base 32. And as maybe we're in a year or two, it's going to be about 56 characters with the next generation of Onion services, making this problem probably even worse. And I don't think it would even fit in that text box in Wikipedia anymore. So clearly there's a need to solve this problem, because at the moment there's no way to label or identify an Onion service in advance. I mean, they're a fantastic tool, but I believe that the growth of at least human-facing Onion sites are currently limited by this issue because of the practicality. So here, the workaround to this over the years has been things like the Hidden Wiki or other central directories. Now these work. These are basically directories of all the Onion sites, and then you can go and find it and click on it, and that works. But the problem with these directories, they must be constantly maintained, and they really don't scale beyond a few hundred entries. But at the moment, this is really the only solution that we've sort of made working in practice. But I think the fact that these exist in the first place suggests that this is an open problem that needs to be solved, and this is why I've aimed at this problem. Here are our objectives for our project. These are the tasks that we wanted to achieve with our project. First of all, we wanted to have anonymous registrations. We know that there are privacy issues with DNS, internet DNS. So in our system, we wanted to ensure that there was no personal information in the registrations, which of course ties into Onion sites. Secondly, that the queries themselves are indistinguishable and not trackable. They're privacy enhanced. Third, that we have strong integrity guarantees. We use cryptography to ensure that things are authentic and there's strong integrity. Fourth, that we have global, essentially one-to-one mappings that names are unique. You can always expect a particular name to go to the same place, no matter where you are connecting to Tor from. Fifth, that there are no root authorities. As we're probably aware, there's issues with having a centralized solution, and certainly that is the case on the internet, where one organization essentially controls .com. Finally, the sixth point, we need to make sure that the system is fast and lightweight. I don't believe most people would use a system if it took a very long time to resolve a name, so it should be relatively speedy. And seventh, and finally, it should be optional. Of course, not all of the Onion sites are applicable to humans. They have many other uses, and so I want to make sure that the system does not break that compatibility. So it's an optional system. We have some, I'm sorry. So this is the problem with this is that naming systems are hard. This has been an open research problem on torproject.org for several years. It was listed as something to solve, and there's been several attempts to achieve it. The reason it's so hard is because it's very difficult to distribute unique and meaningful names without one central authority distributing them. There's been a few attempts at this over the years, though. We may be familiar with Shallot, which simply regenerate an RSA key over and over again until you have a desirable noun at the beginning of the name. So some popular examples for this are Facebook, which made the somewhat suspicious name Facebook core wwi.onion. They just brute forced that until they found one that worked. But this approach only really works for 8 or 9 characters before the name is too big to brute force. So that's been one approach that has some popularity. We also have a system, Namecoin, has been out there for several years. Early fork of Bitcoin. I could talk about this later, but essentially it uses a blockchain system. The trouble with this is it's very hard to anonymously acquire Namecoins and use them to register a name, which makes the whole registration process very difficult to be privacy enhanced. So we also see DNSSEC, which is a system for internet DNS. And recently there was some talk about Blockstack on the TorDev mailing list. Proposal 279 is a naming system for Tor Onion services. Due to the number of attempts at this problem and everybody sort of hacking their own solution together in the Tor browser, thankfully several people got together and made a nice API that hopefully will be available for everybody to use. But interesting from that proposal, there's a line that says, we believe that the UX problem of non-human memorable addresses is not solved with the above solutions and remains a critical usability barrier that prevents Onion services from being used by a wider audience. And I definitely believe that to be true. So this is our contribution. We have made a practical DNS for Onion sites. It has a decentralized design. It's powered by the existing Tor network. We are recycling that infrastructure for our own purposes. Requires no changes to the little t Tor binary. It has strong integrity guarantees and is resistant to node compromise, denial of registration, and land rush attacks. And as you can see here, it works inside the Tor browser, and by dropping a few files into the Tor browser, it works out of the box at startup. So it is relatively easy to integrate into this existing system. So our fundamental building blocks, we have several cryptographic functions that we rely upon, and we also have some architecture of our data structures. So we rely upon a cryptographically secure pseudorandom number generator, both a beacon and a function. We use digital signatures, which is RSA for the current Onion service system, and EDDSA for the next generation. And we have a proof of work function, which is currently SHA-2. As part of, I want to point out there's no encryption functions, so that all data and processing is public and independently verifiable. The trade-off to this is, of course, zone enumeration, but I consider this a minor issue and worth the trade-off. As our fundamental data structures, we of course have a domain name as one of our fundamental units, and we have chosen the .tor top-level domain, which we consider to be relatively intuitive. It's not on the existing DNS system, so it should be available for our purposes to catch that lookup. To register a domain name, we use a structure called a ticket, which contains your name, subdomains, some proof of work, and a digital signature. Our name servers are called mirrors. These are the name server that has a full copy of the database. All tickets and all registrations are available in a mirror. We have a thing called a quorum and a quorum candidates. Quorum candidates are up-to-date mirrors that contain the latest copy of the database, but they're also a fast Tor relay. So you can check for certain flags and certain consensus weight to ensure that they're sufficiently fast to handle these additional duties. One of our fundamental structures is also the quorum, which is a short-lived subset of quorum candidates. And we use these as the, some of the authoritative systems in our architecture. So here's essentially the data flow, and there's this diagram in our paper. So I want to explain all these in detail, but essentially the flow of our system is that we use the Bitcoin network to generate a secure random number. This happens every 10 minutes, and you can extract up to 32 bytes of random numbers from it. We then use that to generate a quorum, and the tickets are then sent to the quorum, and it's replicated across all mirrors. The quorum then publishes the Merkle tree root in their router consensus, and then the client can verify the responses by gathering all this information and confirming that everything is valid. The quorum is, as I mentioned, authoritative name servers. Like all mirrors, they maintain a sorted list of tickets, and they build a Merkle tree. They then publish the root hash in their relay descriptor, and the largest agreeing set is considered the authoritative hash representing the master database. Since this root hash appears in the consensus documents, it's easy to compute the quorum retroactively or at any given moment. And this makes it decentralized. Because these are rotating periodically about every. These are rotating periodically. So we've chosen a rotation of about a week, and about 127 of them, and we proved in the paper that this is a good balance between the size and the security of our system. So in the registration process, first the unit service administrator would create a ticket. They would then perform some period of proof of work, and they perform a minimum amount of work. But the more work they perform, the higher the chance they have of winning a name. They then work on this ticket on the proof of work for up to 24 hours, and then they commit the ticket to the quorum within a narrow window of about 5 minutes. After the commit, the onion service then reveals their ticket to the quorum, who examines all the tickets and performs a weighted selection. A lower value to the proof of work means a higher chance of selection, and a requested name is only selected once, so there's no duplicates. In this way, in this lottery system, attackers are forced to compete directly with honest users and are forced to either focus their efforts or spread it out across many names. In either case, honest users will always be able to win names because it's a probabilistic scheme. To do a query, I've essentially inserted the binary into the Tor browser, modified the Tor browser files so that my software listens for .tor requests. It talks to the Tor control port and listens for these .tor top-level domain. And once it has this, then it queries the mirror for a record and a subtree. And if the mirror says 404 not found, like I don't have this name does not exist, then it can verify that. This is possible because of the Merkle tree, and I can achieve authenticated denial of existence. Once that is the case, then I can resolve it into an onion address, rewrite the request, let Tor auto attach it to a circuit, and then I can load the Tor browser under a top-level domain. So it has the appearance of this working under the hood. So the security of the system, I did some extensive security analysis of our different aspects of our system. Merkle tree, as I mentioned, prevents the servers from lying, and they cannot spoof a record or claim that it does not exist. We've shown that even in the current distribution of consensus weight in the Tor network, it's still safe to choose 127 Tor nodes, and that our lottery system prevents CPU-powerful adversaries from completely taking over our system. And no matter how much power they have, there's always a chance that honest users can still win. And furthermore, by choosing a set number of names, we have limitations against land rush attacks. And we also showed and cited a paper that demonstrates that Bitcoin is a safe random number generator. So I'm short on time, but in action, we have a working prototype that we have deployed. It uses JSON RPC for inter-server communication, and we were able to load our example service. We can do prefetching and caching to ensure that the lookup is always instant. But otherwise in practice, we did some experimentation and found that the rewrite and lookup would take about half a second. In the lower right, you see an example of the Onion service software that has a menu and helps the administrator manage cryptographic details. And this is the word translation of a EDDSA key that I've been working on. So where are we now? We've completed a good chunk of our software. We've got full support ready for 224, proposal 224, which is the next generation of Onion services. We support several packaging, and we've decentralized, and we're still working on decentralizing our server. Due to the issue with SHA-1, we're going to be waiting until proposal 224 is ready to go before we deploy it. Other than that, we have this ready to go. We're just finishing it up. I'm rather short on time. Do we have any time for questions? Let's see. I think you were first.
Is there anything that would prevent me from putting up my random service and registering it as Facebook.com?